Hi guys, this is where we left off. So we're going to talk about strong acids and weak acids, and then strong bases and weak bases, and then we're going to go into a little bit of the equilibrium that we learned from chapter 15 into acids. Okay, so a strong acid is going to be a strong electrolyte, which means it completely ionizes, which means breaks apart. Okay, hopefully you remember that from chapter 8. And then a weak acid will be a weak electrolyte, and a very, very small portion is going to break apart or ionize. Okay, the weak ones are always going to have this double arrow. A strong one will always have a single arrow. Okay, it's going to be the same for strong bases. They're going to be strong electrolytes, and again, they're going to completely ionize or break apart. And then a weak base is going to only partially ionize, and again, they'll still have that double arrow. All right, so some trends in acidity. We kind of already talked about this, but the stronger the acid is at donating a proton, the weaker the conjugate base is, so that's new. Also, a higher oxidation number will make it a stronger oxyacid. If you don't remember oxidation numbers at this point, it's okay, but they will reappear in chapter 19, so we are going to need to relearn them. Okay, and then a cation acid will always be stronger than a neutral acid, and neutrals will be stronger than anions. Okay, this is just in ranking. I'm probably not going to ask you either of those, but, well, I will ask you about the acid. If it's a strong acid, it'll have a weak conjugate base. Okay, so now we're talking about Ka, and this is the same K from equilibrium, but now we're talking about the equilibrium constant of acids specifically. So if the Ka is greater than 1, remember that means it lies far to the right towards the products, which means it nearly 100% ionizes, or it does. It also means the strong acid is the H plus concentration, and you are going to need to make sure you know these 6 strong acids. Okay, if you know those 6 strong acids, everything else is weak. So make sure you know them: hydrochloric, hydrobromic, hydriodic, nitric, perchloric, and sulfuric. Okay, weak acids are going to have that Ka less than 1. And it's only going to partially ionize, which we already talked about. Okay, the weak acid does not equal the H plus in the solution. So for a strong acid, it was equal to. For a weak acid, it is not. And if you look at the image here, so we've got a whole bunch of hydrofluoric acid in here, but only 2 of them broke apart. So it very partially ionized. Really, normally it's just even less. I do want you to know the larger the Ka, the stronger the acid. Okay, and then the smaller the Ka, the weaker the acid. And we're talking about these having very small exponents on their scientific notation. We'll look at that in a minute, but this is super important. Okay, so notice here it's asking about the farther the equilibrium position lies towards the products, the stronger the acid. So here we've got a Ka of 1.1 times 10 to the negative 2, and we've got one of 4.9 times 10 to the negative 10. This one is a larger Ka, so this one is stronger. You will need to be able to do that and determine which one is stronger or which one is weaker. Okay, here we've got our acid ionization constant. Again, it's the same as the equilibrium constant before, except now it's for acids. And it is still products over reactants, and we don't include liquids like before. So we just put our products over our reactants. Okay, here's just a list of some common weak acids. Really, I don't even see any. Yeah, all these are weak. Notice their Kas are all less than 1. Okay, something that's super important is the word amphoteric. We kind of saw this with water earlier in our last video, that water could act as an acid or a base. Okay, and really if it has H plus to lose and a spot to gain, an H plus. So sometimes, and this is always a common question that's missed by my students, I ask which one of these is amphoteric or even which one of these is not amphoteric. But if it doesn't have any hydrogens, it can't be amphoteric because it has to have one to lose. And it has to have a spot to gain. So sometimes students tell me that NH4 is amphoteric. Well, it's not because there is no NH5. Okay, that's not a thing. NH3 is amphoteric because it could lose one and go down. So it's just a matter of knowing which way it goes and making sure you know, is it amphoteric, is it not? Okay, and this autoionization is going to lead us to Kw. Now, Kw, this is a very important equation, we'll use it. And Kw is constant, 1 times 10 to the negative 14 at 25 Celsius. We normally use 25 Celsius as our room temperature, so don't worry about the temperature. As long as everything's the same, it's okay. Okay, so Kw is the hydronium concentration times the hydroxide concentration. Also remember, those brackets mean molarity. Okay, so in a neutral solution, we're looking at hydronium and hydroxide being 1 times 10 to the negative 7 molarity. In an acidic solution, the H3O plus is greater. And in a basic solution, the OH minus is greater. Those are kind of not hard topics to understand. Yes, I've got more concentration of my acid, so it's acidic. I've got more concentration of my base, so it's basic. If they're equal, then it's neutral. Okay, so we're going to use these in calculations. Remember that Kw is equal to H3O plus times OH minus. So to get OH minus, it's Kw over hydronium. And then remember, Kw is 1 times 10 to the negative 14. So for A, we're looking at OH equal to 1 times 10 to the negative 14 divided by 7.5 times 10 to the negative 5. And I get 1.3 times 10 to the negative 10. Don't forget your unit. And then it asks, is it acidic, basic, or neutral? So this is less than the hydronium. So this is basic. Okay, B, we're going to do the same thing. It's always going to be 1 times 10 to the negative 14 divided by whatever the other one is. Okay, I get 6.7 times 10 to the negative 6. So now we're looking, is the hydronium bigger or is the hydroxide bigger? And I wrote that first one wrong. It's this one is acidic, and then this one is basic. I'm sorry. Okay, C, if you notice, 1 times 10 to the negative 7, that is neutral. You should not even have to determine what the OH is, because when it's 1 times 10 to the negative 7, they're equal. So OH and hydronium are 1 times 10 to the negative 7. Okay. I'm going to do one of these. I'm going to do the bottom one. So using that same equation, you rearrange it and you get Kw over OH. Just notice that Kw is always on top. So for C, I've got that H3O plus is 1 times 10 to the negative 14 over 8.2 times 10 to the negative 10. And I get 1.2 times 10 to the negative 5, which means this is acidic because our hydronium is a larger number than our hydroxide. So just make sure you can do these. They do get easier with time, so don't worry about that. Now we're going to talk about pH, which is really what most of us are used to hearing about. Maybe if you have fish or you have a pool or a hot tub, something like that, your pH has to be the correct number, otherwise your fish die or your pool is off and all that. So it is super important to know these two equations. The pH is equal to the negative log of the concentration. And then the other equation to go the other way is if you have the pH, you press second log on your calculator and it comes up with this 10 to that, and you just type in negative pH. I'll show you in a few minutes. When pH is less than 7, that's when we're an acid. You do need to know all this. When pH is greater than 7, that's when we're a base. And at 7 is neutral. As we go out from 7, the farther it is from 7, the stronger it is. Okay, so if we look here, our stomach juices, those gastric juices, could be all the way down to 1 pH, which is a super strong acid. And then soft drinks are 2 to 4, which is why they kind of ruin your enamel on your teeth. Okay, but as you notice, most things that we ingest are acidic. Most things that are basic are not. Remember, I talked about most of them being cleaning products. Strong acids and strong bases are equally corrosive, so they'll eat through different materials. But the closer you are to 7, the more neutral you are and the less strong. You're a weaker acid at that point. So I have a couple scars on my hand and my foot, actually, from lab through the years. So I got a scar from a 3 molar acid that was actually a negative value because pH scale does go a little bit lower. And I also got one from a 6 molar acid, which is also that close to -1. So both of which, I mean, it'll even burn your skin, and it's been many years since I was in college that these happened. I would say one probably happened in, I don't know, 2010, the ones on my foot. And the ones on my hand, I don't know, 2015, but they're both still there. And so just make sure if you're using stronger acids, which y'all don't really have access to at this point, you're careful with them. Okay, so here's what I was talking about. So close to here, we're more neutral. As we go farther out, we get stronger for the acid. Same thing here, we get stronger. Okay, so now it just wants us to calculate the pH or from the OH. So remember, pH is negative log of hydronium, or H. Okay, so on A, we can just take the negative log of 1.8 times 10 to the negative 4. And I get 3.74. Okay, the general rule of thumb I'm going to say on pH is just have 2 after the decimal. For B, though, I have OH. So first I have to find H3O+. And I do that by doing KW divided by OH. Okay, and I get 7.7 times 10 to the negative 13. So then I take the negative log of that. And I get 12.11. Okay, don't forget it also asked about, is it acidic or basic? Remember, less than 7 is acidic. Greater than 7 is basic. Okay, if you have questions, I have lots of practice if you need them. I'm going to do one more like the base. So for B, I'm going to find H3O+ first. Remember, you got to do KW divided by our OH. And I get 1.4 times 10 to the negative 12, and then I take the negative log of that. And I get 11.85, which is basic. Okay, if you have questions, please let me know. Okay, now we're going to go the opposite way. Remember to find concentration from pH. We're looking at 10 to the negative pH. So I do hydronium is 10 to the negative 4.80. Also, pH does not have a unit, but concentration does. So make sure for concentration, you put a unit. Okay, there's one more. So I do 10 to the negative 8.37. And it is 4.27 times 10 to the negative 9 molar. Don't forget, concentrations have units. Units are super important, y'all. Okay, and then there's OH, which is just related to POH. So before we did OH to hydronium, and then we did the pH, but now we can go this way. So negative log of OH will give us POH. The opposite gives us OH. One thing you need to keep in mind is that pH and POH are going to equal 14, always. So if you can find one, you can find the other. Okay, there's that equation. They did the whole deriving it, but that's not necessary for y'all. All right, so now we're going to talk about pKa and pKb. Y'all, if you see the small p, it means take the negative log of whatever is after the p. So pH is take the negative log of H. POH, take the negative log of OH. pK, take the negative log of that K value. Okay, so the larger the Ka, the smaller your pKa will be. So the stronger the acid, the smaller pKa. And remember, that's kind of like less than 7. The stronger the base, the smaller the pKb will be. I am going to post a table of those constants, Kas and Kbs. All right, then we have percent ionization. This just means the higher the percentage, the stronger the acid, because that means it's ionizing more. Okay, and this is what you need to know for that equation. There will be one on your quiz or your test. And I believe there's one on the homework as well. So we're looking at the equilibrium value, which comes from our ICE table, the initial value, which is given, and then our times 100 because it's a percent. Please, times it by 100. All right, this is just going through some basic stuff about the KW and how it's related. Okay, so when we are finding the pH of a strong acid, if it is monoprotic, meaning it has one hydrogen, it's equal to it for those strong ones. If it's diprotic, the first ionization is all we care about, so it's still equal to it. We don't care about the second ionization, though. And ionization is when the hydrogens are coming off. All right, so find the H concentration of a 0.1 molar hydrocyanic acid. Okay, so this notice is a weak because it is not one of the 6 strong. So when we have a weak, you're going to need an ICE table. Okay, I'm going to pull it up. You've got to be able to write these equations, and I know the homework has going through that, and for some of you, it's going to be really frustrating because if you don't put the states of matter correctly or you don't do the spacing right, it's gonna take off some points, but it'll be okay, y'all. There's extra credit built into every homework. Okay, so we plug our values in. They gave us this initial value. We do our plus x minus x. Remember, the minus x goes away because it's small. So when we do Ka-ICE tables, it's always going to be Ka is equal to x squared over whatever the initial value is. because we're not starting with anything else. Okay, the reason I walked through this way is because it gives you the Ka. In the event it doesn't give you the Ka and you're not searching for the Ka, you need to look it up on the appendix that I'm going to post in week 3. Okay, once you do that, you solve for X. And remember, X is molarity because it's that concentration of H3O+. Okay, so here's another, remember that ionization Ka table that they gave us. I just want another one. Okay, so hydrofluoric acid. I am going to write the Ka value down for that. It is 6.8 times 10 to the negative 4. Okay, so I've got Ka is equal to x squared over 0.25. These, again, they're the easiest ones, and then our Ka is 6.8 times 10 to the negative 4 is equal to x squared over 0.25. So now all we do is solve for x. I get that x is 0.013 molar, and that is our H3O plus concentration. Okay, so now we're finding the pH of an nitrous acid solution. So I'm just going back, finding nitrous acids, Ka. I'm going to write that. So Ka is 4.6 times 10 to the negative 4. Okay, so I've got 4.6 times 10 to the negative 4 is equal to x squared over 0.2. Okay, remember, this is not pH. This is our concentration. X is concentration. So then you have to take the negative log of that. So I get that the pH is equal to 2.02. So this one has a few more steps, but it's really not so bad. You don't have to do the ICE table in this chapter, which is great. But don't forget how to do them because they're coming back in 17, and then 15 is on the test as well. Okay, so they do the whole ICE table thing. Now we're going to do acetic acid. I think it's 1.8 times 10 to the negative 5. That's what I thought. Okay, so its Ka is 1.8 times 10 to the negative 5. And that's equal to x squared over 0.015. So we just solve for x. It's 5.2 times 10 to the negative 4 molar. And then it said pH. So you take the negative log because this is H3O plus. I get 3.28. Again, if you have questions, please let me know. Okay, remember, I'm not doing any where this approximation doesn't work. So if you want to walk through this, you can, but you've got to use a quadratic formula, which we will not be using. Or you hope it's a perfect square. Okay, so now we're finding the equilibrium constant from pH. This is a little different. You may need the ICE table here. Just remember that this is, you can find H3O plus from this. So if they give you pH, that's the first thing you should do. So we take 10 to the negative 4.25. And I get 5.62 times 10 to the negative 5. Okay, so HA is going to break into H plus and A minus. I know that this is 0.1. I've got nothing there. I've got minus x plus x plus x. Okay, this value is x. So from that, I know that Ka is H plus times A minus. This is just the generic expression. Okay, and I've got all my values. I've got my 5.62 times 10 to the negative 5. And because that's x, and I've got 2 of them on the top. And then on the bottom, I'm going to do 0.1 minus 5.62 times 10 to the negative 5. Make sure you put that in parentheses. You don't want to get the answer wrong because of that. Okay, and I get that Ka is 3.2 times 10 to the negative, really it's 3.16 because of sig figs, times 10 to the negative 8. Ka's do not have units. Neither does K, neither does pH. Okay, so they're going to walk through the whole thing. There it is, 3.1 times 10 to the negative 8. Okay, one more we're going to do this way. I've got, again, basic ICE table. I've got 0.175 minus x, 0, 0 plus x. Okay, so this is x. So I've got Ka is equal to 5.62 times 10 to the negative 4 squared over 0.175 minus 5.62 times 10 to the negative 4. And I get Ka is 1.8 times 10 to the negative 6. Okay, so you can't ignore the minus and plus x when they give you x. You ignore it when you're finding x. Okay, don't forget our percent ionization. We're almost done with today's video. So find the percent ionization. To do that first, we need H3O plus. So remember, it's H3O plus over HA times 100. Okay, I already have HA is 2.5. Okay, to find that H3O plus, I need to do my x squared over 2.5 is equal to, they're going to tell me, 4.6 to the negative 4. So H3O plus 0.034 divided by that 2.5 times 100. So this percent ionization is 1.36%. That's how much it breaks apart. Very, very small. I can't see that right now. It looks like 0.25 of acetic acid, but my little recording screen is right over that. So if you need help, let me know. Okay, so this is where we're going to stop today. Y'all have a great day, and we'll continue probably tomorrow.